Hello everyone, and welcome to our online series of course in which we were studying machine control systems, uh, and we were recently studying chapter number 7, root locus design and root locus sketch. So this is the third video in which we were studying the root locus sketching techniques, and we have previously studied in the last two videos rule number 1, 2, and rule number 3. So in this lecture we will study rule number 4 and finally rule number 6 to summarize the overall uh, aspects of root locus, and we'll later see with some of the small points or small observational rules at the very end of this lecture. I will summarize and close this lecture in this video. So let's start with rule number 4. So rule number 4 is basically a graphical method to check that a given point lies on the root locus or not. So like, for example, in our basic calculus and basic algebra courses, you remember that if there was a line, and let's say if that line was y equals mx plus b, and if a certain point lies on that line, so that result would be equals to greater than 1 for y. If it was equals to 0, though, so that we were always saying that the point lies on the line, and if the result was less than 0, we would say it's below the line, and lastly if it was greater than 0, then we would be saying that it's above the line. So we'll use the same analogy and technique for root locus as well. So we'll call a given point, or that, let's say it's a design point, right? So what is a design point? We will study in the next part of this chapter 7b. So let's take it for now as a point. So let's say this is a simple point which lies on the root locus. So if the point lies on the root locus, then it should satisfy its equation. That's a simple thing, right? So let's see how we can verify that if a point A lies on the root locus or not. So we have to develop mathematical or analytical foundations for that. So let's begin. Consider this function, a plant function in which we have four number of poles and was 0. And if I want to check that if a point A lies on the root locus or not, so what I'm going to do is I'm going to assume that, let's say if A is a point which is A is equals to x comma y, in which y represents the imaginary axis, is a point on the S plane, right? So this is a point on S plane A, and I want to check that if that point lies on this point, right, lies on the root locus or not. So what I do is that I take this plant function, and if I say there is a value k associated with that as a proportional gain, right, so I can associate a k here, and I can substitute the values of this point in the place of this s, and I'll eventually get this result, right? So I'll have x plus jy, and I can substitute all over wherever s to replace this value. And of course we all know that for the case that this is actually your Cartesian coordinate representation, Cartesian coordinate representation, and if I want I can convert it into you can say the polar representation. So what is a polar representation and what is a Cartesian representation? So let's say in a plane I have a value x, right? So a point, random pointed here, So I can say that this point is actually x comma y, and I can say that x is the horizontal distance and y is the vertical distance, x is your horizontal distance for this. So the resultant would be your r, right? And everybody knows that r is equals to under root x squared plus y squared, right? So don't mind my y. And for the same reason, let's say there's some angle here, so I can write it theta equals to tangent inverse of y upon x. And when I have r and theta, I can write as r angle theta, which is your polar representation, right? So this is how I convert a rectangular component, or you can say the Cartesian coordinate plane, to your polar coordinate. So that's how I converted all these points into polar coordinates, and these are the magnitudes and these are the angles. And for that reason, you can uh, sum up, you can apply the properties of polar coordinate systems, right? And let's say these are the magnitudes. Vz1 is the magnitude of the location of pole, and towards that you can always use the properties of polar coordinate systems, which are you can multiply the magnitudes and divide the magnitudes respectively. Let's say for example, um, these are the magnitudes of these polar coordinates, so these can be individually multiplied, so all of the numerator magnitudes in the numerator gets multiplied, and this whole product get divided with the all of the magnitudes present in the denominator, right? And all of the angles can be held up accountable that in such a way that all of the values of these would be added together, right? So all of the angles in the numerator would be added, and all of the angles in the denominator can be subtracted to the all of the angles in the numerator. So this is basically the fundamental property which we have already seen in calculus 1 course. So you can always revisit it by using this simple expression, which was your characteristic equation of the basic transfer function 1 plus k g naught equals to 0, which we have seen in our previous lectures. We can derive it for this value k g naught, and this will equal to 1, which is if this equals to minus 1, which I can say that 1 is the magnitude and plus minus 180 degree is the angle. So whenever I have a kg naught function, which is the open loop gain, equals to a magnitude of 1, and whenever you have an angle of plus minus 180 degrees, so this is actually the condition on in which the point A would lie on the root locus, right? So it's quite simple, is that whenever you substitute that point into the equation and into the polar coordinates and you solve it, and if you get the result of kg naught as one magnitude and plus minus 180 degrees as an angle, so we can say that that point satisfies your root equation of root locus, thereby saying that that point lies on your root locus as well. By saying that, and by uh, concluding that using these properties, that magnitudes in the numerator get multiplied and all the magnitudes in the denominator get divided from the numerator, we can and same forth for the respectively for the angles, we can derive two more rules and two more laws, which won't be too much useful in design in basically sketching, but that would be useful in design. So for that, let's move forward, and I can write it if all the magnitudes including the k, it's again, so in the numerator and denominator gets multiplied all in the numerator and divided with the magnitudes in the denominator, if that comes up equals to 1, which is the magnitude of the point if point lies on the root locus, and if sum of all points in the numerator minus the uh, angle in the denominator is equals to sum of all these equals to plus minus 180 degrees. So I can say that if these two rules can be individually called as, the first one can be called as the gain criteria or gain rule. Uh, preferably we can call it gain criteria, because we have already seen the rules, and so let's not confuse with the nomenclature. And for angles, we can say that the second rule or the second criteria would be your angle criteria. The sum of all the angles of the poles less the angles of the zeros would be equals to plus minus 180 degrees. So this would be angle criteria, and this would be your gain criteria. And I find these values of 1 and plus minus 180 degree from the deduction of this derivation from this characteristic equation. All right, so yeah, that's it for rule number 4, that if a point lies on the root locus, so in order to find that out, if we substitute that point into the open loop transfer function kg naught, then we will be having one angle plus minus 180 degree. Only in that case that point lies on the root locus, otherwise it doesn't lies in the root locus. That's sort of a graphical method to check that a given point is present on root locus or not, right? So we usually use this point to find our designed point. So we'll see in the next lecture what's the design point and how to verify that. For now, let's move to next rule, as we have discussed previously, that the definition of breakaway point and break-in point. So breakaway point is basically the point at which the root locus leaves the real axis, right? For example, in case of sigma 1, we can say that both of the root locus from each of the corresponding pole at -1 and -2 collects at this breakaway point and then departs at different values, right? So they depart away from this breakaway point. So this point from which the root locus leaves the real axis is known as the breakaway point, and the point at which these uh, uh, root locus meet or collects up to the real axis, or you can say the root locus returns to the real axis. So these are like going away from the axis, and then at this point they are collecting back to the real axis, or you can say they're returning to the real axis. This point is called the break-in point, right? So we'll see how to calculate the breakaway and break-in point. So we have seen previous examples in which we have seen breakaway points and breakaway points. Sometimes we have just breakaway points, sometimes we have breakaway and break-in points together. And when we have a circle, case of circle, right? So how to calculate those exact points? How would I know that this point lies here but not here but not here? So how I have to know the exact position of these points? So let's see how I can calculate the breakaway points. So if you can see, the breakaway points seem to have when root locus drastically rise in its slopes, right? So you can see here its slope was 0 and suddenly its slopes gets up to infinity, right? Because it's going exactly to the parallel to the y-axis just before leaving the breakaway point and break-in, right? So I can say that I want to find out, this is my characteristic equation. I derive this for value of k, let's say, and I call this some polynomial p of s. And for break-in and breakaway point, I'll check the rate of change of uh, k is equals to 0. So that's the condition for relative maximum, if you remember, right? So I'm calculating the maximum value for which the k is equals to. So the slope is equals to 0 when you have such situation, right? So simply you can substitute this function here and you can calculate the values of k, and you can find the breakout points. Let's see an example to demonstrate this, what I'm trying to say. Let's say we have a plant function, right? We have two poles at -2 and -4, and let me drive this, substitute this g of h into this equation, and I'll assume that it's a unity feedback system, so h of s is equals to 1, and I'll drive this for value of k, or I can directly substitute it 1 upon g of s. So I will get this value, and I'll drive this for value of k. I'll get these factors, and then I can take assign this as e of s as another polynomial and take derivatives for it. And when I find the derivative, I find it simply a value which indicates the position of the breakaway point on the real axis. So on the real axis between 2, -2 and -4, there is -3, which is indicating that between -2 and -4 at -3, both of the roots poles are collecting up and then they are breaking away from each other at s equals to -3. So how do we know this is a breakaway point but not a break-in point? So it's quite obvious. Whenever you have a negative s, that means you have a breakaway point, and whenever you have a positive value of s, so you will have a break-in point. So you can see the demonstration here, like, so it's a -4 and -2, and of course we have -3, so they are collecting up to here and they are splitting away, and this is your breakaway point which you have computed at s equals to -3. So this is an example in which there is one more thing additional, that there is also a break-in point mentioned here. So what's difference is, there's nothing too much complicated, just for your uh, practice, that I have a open loop function here, and I drive this value for k as I did in the last case, and I have these values here and I take derivatives, right, for k, and I'll find the values of s. So we have a value sigma here, so let's consider it like s. In the last case it was sigma here. So when I find out the values of sigma, it's a quadratic equation. I'll get two values, one a negative one and a positive one, and the negative one indicates the breakaway point and the positive one indicates the break-in point, right? So it's going to be a more likely a circle in which at this point the poles are collecting in to break away, and then apart are collecting up at 3.82 to form a circle, and then went one pole went to the zero and one pole will approach towards the hypothetical zero at infinity, which as we have seen earlier. So you can I always encourage to draw root locus for this diagram as well, so you can have a basic perception of what's going on. Yeah, so try to draw the exact root locus for this case. So that's it for all of the rules, and some quick rules and quick observation. You can say that we already knew that all of the roots which we have seen to appear in complex form will appear in the conjugate form. So if you remember that in the last in chapter 3 we have seen that uh, there was s equals to sigma plus j omega t. So it was plus minus. So unless the values of sigma and omega d changes, which actually do not changes for a root, so actually in any form these roots will be conjugate pairs of each other, right? So they will appear always in the all of the poles would be, or the roots would be appearing, if they are complex they would be in conjugate form. Second point would be, at no time the roots will be crossing over paths. So we have already discussed about this point, that no root locus will pass over another root locus, or you can say that they will not for a particular pair of pole and zero, the root of a root locus, that root locus will not pass or intersect any other pole or any other zero, apart from the zeros and poles it is directly affiliated with. And then we'll come to the third point, that if there are enough poles and zeros to make a pair, then the extra line goes to infinity. That is the loss friend, right? So we have already discussed that. If we have a missing zero pair for a zero, a pole pair for a zero, and a missing zero pair for a pole, so we'll assume that that particular pair is at the infinity, or a lost friend, or you can say the song of strings if you like to say the lost friend. And then we can move to last point, that if there is at least two lines going to infinity, then the sum of the all roots at every value of k is constant. So actually if the lines are going evenly, and the sum of the roots on the line would be equals for every value of k, and we have verified in the first lecture that those values will be same. Now, that's it for today, but I'll leave you with one assignment to reflect back and think about it, which is we have this transfer function or plant function, which we have two pole at -10 and -1, and I have drawn this root locus. Of course, you can assume that, not assume that, but you can also anticipate that would have solved this for angles and centroid, and I would have find the centroid here, somewhere like here. No, somewhere like here. No, it's exactly here. And then I would have seen that the angles would be pi by 2 and minus pi by 2, or you can say 3 pi by 2, and I would have this structure. So the only thing that I want you to think about is if I add additional poles, like I add a simple s here to add a simple pole here, right? So what could be the effect of adding an additional pole to the system, or on the root locus, right? So what is the effect of adding an additional pole or an additional zero to the root locus? So what happens to the root locus when you add an additional pole and zero to this existing system? So let's say you have to sketch and observe for if I add 5 upon s and get multiplied with this, right? So there it adds up, this s adds up an additional pole, right? So what happens to root locus? You have to see that and reflect me in the next class what happens to this sketch when you add a additional pole, and what happens if you add an additional zero. So you have an additional zero, s equals to 0 here. So what happens to the system, to the root locus, when you add an additional zero? So yeah, think about it, sketch it, whatever you can see about the textbooks and the online resources, and let me know what feedback you have in the next class, right? So that's it for today. Thank you for joining in.